on the overall cycle efficiency. Then we will discuss two problems. One is related to the basic Brayton or Joule cycle, and the second one will be related to the efficiency and work ratio related to compressor and turbine efficiency. In this manner, we will proceed. So we will start with the introductory part of gas turbines. We have discussed heat engines in many forms in thermal engineering. I think up to 5th module, you have discussed different types of heat engines. The machines which convert heat of chemical reactions into mechanical work are known as heat engines. The following heat engines are actually familiar to you, the first four, because already you have studied these things: steam engines, steam turbines, diesel engines, gasoline engines, then gas turbines. Out of these, the first two are external combustion engines. The next two are internal combustion engines. And the last one, gas turbines, which can be internal or external combustion engines. But most of the cases, it will be internal combustion engines only. Now, we are having what is a gas turbine, or what is the importance of gas turbine? A gas turbine produces immense energy from a compact unit. That is the most important thing related to a gas turbine. So it finds many applications, especially in the field of aviation, oil and gas industry, power generation, and marine propulsion. You can see many types of gas turbines used in these particular fields. As I mentioned, most of the gas turbines are internal combustion engines. Next, we are having the components and working of a simple gas turbine system. In a simple gas turbine system, as in the figure, we can see that, one second. You can see that there is a compressor. To the compressor, there will be suction of air. Then, one minute, okay. There will be suction of air, and it is getting compressed. Then, there will be combustion chamber. The compressed air is actually flowing to the combustion chamber. Fuel is added to the combustion chamber. Then, inside the combustion chamber, there will be air-fuel mixture. The air-fuel mixture is then flowing to the turbine. When it is reaching the turbine, there will be high enthalpy or heat content for the fluid which is entering the turbine. So there will be an expansion process. During the expansion, the air-fuel mixture getting expanded and work is produced. That work is the mechanical work which we are getting. Another important thing we have to understand is there is turbine and compressor. How the compressor works? Compressor need some energy because all the compressors should have a prime mover. Normally, the compressor will be connected to the turbine using shafts. So a part of energy which is produced by turbine is used by the compressor. Now we will classify the gas turbines. Here the gas turbines are classified based on their operation. The first category is actually open cycle gas turbine. Already we have seen the operation of this open cycle gas turbine in the previous slide. That is, there is a compressor, air is sucked by the compressor, then it is moving to the combustion chamber. There will be air-fuel, mixing of air and fuel in the combustion chamber. Then it is flowing to the turbine. work is produced. From the turbine, the exhaust is going to the atmosphere. Now, in the case of closed cycle gas turbine, all the first three parts are the same. There is compressor, heat exchanger. The heat exchanger is exactly the combustion chamber. It is given as a heat exchanger, but it is combustion chamber. You are supplying heat. Then in the turbine, there will be expansion. After the expansion, the exhaust gases are again going to the compressor. So that is a closed cycle gas turbine. There is another classification. It is based on the combustion process. The combustion process can be constant pressure gas turbine. The combustion process can take either inside the combustion chamber at constant pressure or at constant volume. Depending upon that, you can call it as constant pressure gas turbine, in which combustion takes place at constant pressure. The other case, it is constant volume gas turbine. Inside the combustion chamber, there will be a constant volume process. So it is known as constant volume gas turbine. Now, what is the working principle of a constant pressure gas turbine? Here you can see inside the constant pressure gas turbine, the first part is a compressor. To the compressor, air is taken. The air is flowing to the combustion chamber. So this is the combustion chamber. I think it is clear to you. Initially, there is a burner. Through the burner portion, only a small portion of air is flowing. The other part of the air is actually flowing through the annular space arranged around the combustion chamber. What is the purpose of flowing the major part of the air through the annular space? Because at the burner, there will be combustion of air and fuel. So the temperature will go, say, more than 1000 degrees Celsius. It may affect the metallic parts. In order to get a cooling effect, you are actually taking the flow in the flow through the annular space, flow of air through the annular space, because large quantity of air at a lower temperature through the annular space will actually cool the combustion chamber. So for cooling purpose, we are having higher quantity of air. Then after the after the combustion chamber, there will be mixing of the air fuel mixture as well as the air which is flowing through this annular space. Both will come to the turbine. Then there will be expansion and energy is produced. Here you can see the coupling between the compressor and the turbine. Here, one thing you have to understand that you have to actually pass more air for cooling purpose also. So 65% to 80% of total work produced by the turbine is used for compression. So the net work output from the turbine system will be less. For higher thermal efficiencies, multi-staging is also practiced. Now we are having the constant volume gas turbine. In constant volume gas turbine, you are having, see, these parts are not important. I am concentrating from this compressor portion onwards. From the compressor, the air is moving and flowing to the combustion chamber through different valves. Say V1 and V2 are the valves used for transferring air from compressor to the combustion chamber. So it is kept inside the combustion chamber. Now there is another valve, say V3, which is for the fuel supply. After supplying the fuel, there will be a spark plug produced, which will actually start the combustion process. During the combustion, high pressure and high temperature will be developed. After reaching a higher pressure, say of the order of 13 to 14 bar, the non-return valve, which is kept here, will get open. So through which the air fuel mixture will flow to the gas turbine. So inside the combustion chamber, there will be constant volume. After the combustion, when there is sufficient pressure, then only there will be flow from the combustion chamber to the gas turbine. That is what the working principle of constant volume gas turbines. The advantages of constant volume gas turbines are they are very compact. The power consumed for running air compressor will be less. As I told only, minimum quantity of air will be taken because combustion is taking place inside the combustion chamber. But they are costly due to automatic valves, and combustion is intermittent, hence difficulty in smooth running. Okay, the first two can be considered to be advantages, but the next two are some of the disadvantages related to the system. Now we will have the Brayton cycle. What do you mean by the Brayton cycle, or what is the importance of Brayton cycle? Like studying any system or analysis of any system, we will go for a theoretical cycle. Here, Brayton or Joule cycle is a theoretical cycle, or which can be used for the comparison with actual situations. So the theoretical cycle consists of say many processes, which you can see here. You can see a PV diagram. This is a PV diagram and this is a TS diagram. You can compare both PV and TS diagram when the processes are explained. So 1 to 2 is isentropic compression in the compressor. So isentropic compression, as we know, it may be an ideal situation. We will see it later. So during this isentropic compression, W in, that is the work of compression or work required for the compressor, is actually absorbed. So 1 to 2 is a work consuming process. The next one, 2 to 3 is a constant pressure. Here you can see this, 2 to 3 is a constant pressure heat addition. So here also you can see that 2 to 3 is a constant pressure process. Along the constant pressure process, there is heat addition. So it is absorbing Q in amount of heat. Normally, what is the quantity Q in? Q in will be actually the CV, calorific value of the fuel multiplied by the quantity of fuel. You can consider that much quantity of heat is actually supplied to this particular system. That is what happening in 2 to 3. In 3 to 4, it is again isentropic expansion. So it is producing work. So it is the work done by the turbine. As I mentioned, work done by the turbine is consumed by the work done for the compressor also, or it is consumed by the compressor also. So work done by the turbine is the total work produced by the system, but we won't get that as an output, or the net output will be different from the work produced by the turbine. Next you can see 4 to 1, it is a heat rejection process that is happening in a heat exchanger, which we have seen earlier. It is rejecting Q out amount of heat. The same thing which I am mentioned here, but I am going to explain different say parameters. That is isentropic compression in the compressor, where P1, V1, you can add T1 also. P1, V1, T1 is changed to P2, V2 and T2. During 2 to 3, there is constant pressure process. So P2 and P3 are the same. Then V1 and T1 are changed to P3 and T3. Here, from 3 to 4, P3, V3, T3 is changed to P4, V4 and T4. And the last process, again, T4 is changed to T1, where P1 and P4 are the same. Or in general, we can say, now we will go for the analysis part. when we will go for the analysis part, it is very simple to remember that, say, 1 and 4 at points 1 and 4 at pressure P1 and 2 and 3 are at pressure P2 because there are only two pressures, P1 and P2. This P2 by P1 is generally called as the pressure ratio. Next, you are having the analysis of Brayton cycle. As in every analysis, we will have to find out the efficiency of the system. How to find the efficiency? Normally, for any system, the output by input is the efficiency. Here already I have mentioned what is the output. It is not the work produced by the gas turbine alone, because turbine is producing energy, but part of which is consumed by compressor. So the difference in these two is the net work done. So that net work done divided by divided by heat input. Already I have mentioned there will be supply of fuel. Fuel and its calorific value will determine, say, what is the heat input. So based on that, you will get the efficiency. Now, already I have mentioned what is net work outdone. Then, based on the first law of thermodynamics for any cycle, net work done is equal to net heat transferred. You have studied this as the first law applied to a cycle. Here you can see the net heat transferred is equal to heat input minus heat output, or Q in minus Q out. What is Q in? Or Q in is actually related to a particular constant pressure process, say 2 to 3. For any constant pressure process, heat input is or heat is equal to mCp delta T. You know that. So for unit mass flow rate, we can say Q in is equal to Cp into T3 minus T2. Similarly, what is Q out? Q out is the heat rejected during the constant pressure process, that is 4 to 1. Constant pressure process 4 to 1. So 4 to 1 is a constant pressure process. There also the heat is equal to Cp into T4 minus T1. Now, we have to find out the efficiency. Already we have seen it is the net work done divided by heat input or heat supplied. So net work done is equal to net heat transferred as per first law of thermodynamics. So efficiency is equal to net heat transferred by heat supplied. So which is equal to Cp into T3 minus T2 minus Cp into T4 minus T1 divided by Cp into T3 minus T2. We have seen how this Cp into T3 minus T2 and Cp into T4 minus T1 are getting. In the last slide, we have seen this. Now, we can see that Cp is a common factor. We can eliminate that because it is in the numerator and denominator. You will have T3 minus T2 minus T4 minus T1 divided by T3 minus T2. Or you will have, say, T3 minus T2 is common for the first term. So it is 1 minus T4 minus T1 divided by T3 minus T2. Here, in this step, you are actually taking T1 outside to get some temperature ratios. When you are taking T1 outside, you are getting it as T4 by T1 minus 1. This T4 minus 1 is changing to T1 into T4 by T1 minus 1. Similarly, T2 into T3 by T2 minus 1. So this is equal to 1 minus T1 by T2. How we are getting this? That is what explained here. Here, from the equation of reversible adiabatic process, you have studied reversible adiabatic. That is, PV raised to gamma is a constant. If PV raised to gamma is a constant, P1 V1 raised to gamma is equal to P2 V2 raised to gamma. And from the gas equation, we know P1 V1 by T1 is equal to P2 V2 by T2. So combining these two, you will get the temperature ratios. T3 by T4 is equal to T2 by T1, which is equal to the pressure ratio, P2 by P1. Already I have mentioned about pressure ratio. P2 by P1, the whole raised to gamma minus 1 by gamma. What is this gamma? This gamma is equal to Cp by Cv. Cp by Cv, which is equal to, finally you will get, it is pressure ratio raised to gamma minus 1 by gamma. So by cross multiplication, you will get T3 by T2 is equal to T4 by T1. When you are substituting this, these two terms are becoming equal. So finally, you will get 1 minus T1 by T2, which is equal to 1 minus P1 by P2, the whole raised to gamma minus 1 by gamma, which you will get is get as 1 minus 1 by Rp. Rp is the pressure ratio raised to gamma minus 1 by gamma. I think it is clear to you. If somebody wants to take the screenshot, you can take it now. I will wait for some seconds. I think we can proceed. This is the efficiency versus pressure ratio, because we have seen that efficiency is a function of pressure ratio. Thermal efficiency of Brayton cycle is a function of pressure ratio. And it is clear that the pressure ratio is, thermal efficiency is increasing with increase in pressure ratio. And you can see that at higher pressure ratios, there is no much difference in thermal efficiency, or the curve is getting flattened when the pressure ratio is getting increased. Next is the work ratio of gas turbine system. That is the efficiency. There is another term, that is work ratio. Why we are going for work ratio? Already I have mentioned there are two works which we are having inside the system. That is work done by the turbine. One part is work consumed by the compressor. So the net output is work done by the turbine minus work done by the compressor. So next we are having a ratio of net work to the turbine expansion work. That is how much you are comparing it with how much the turbine is producing. So work ratio is equal to net work done divided by turbine work. Already I have mentioned this. Both the compressor and turbine are steady flow devices. So how to get the work done by the turbine or compressor? So in order to get the work done by the compressor or turbine, you should have, you have to remember the steady flow energy equation, which you have studied in basic thermodynamics. There we have seen that for any turbine, when you derived a steady flow energy equation and you have applied it to a turbine, there you have seen the work done by the turbine will be equal to the change in enthalpy plus change in kinetic energy plus change in potential energy and the heat associated with that. But here it is an adiabatic process. Since it is an adiabatic process, the heat transfer is 0. And the velocities are almost the same, so the kinetic energy term or change in kinetic energy is approximately 0. The height is not playing an important role in this particular problem, or it is negligible. So the potential and energy term, that elevation part, can also be negligible. So the final work done will be equal to the change in enthalpy alone. Now, when we discussed about Cp, we have studied that Cp is the rate of change of enthalpy with respect to temperature, or change in enthalpy is equal to Cp into temperature difference. So H3 minus H4 is simply T3 minus Cp into T3 minus T4. T3 is the higher temperature and T4 is the lower temperature in the case of gas turbine. For a compressor, how much is the work consumed? That is W in. So W in is equal to H2 minus H1, where it is Cp into T2 minus T1. Similarly, what we have done for turbine for finding the work output from the steady flow energy equation, the same thing you are applying for compressor also. You are getting Cp into T2 minus T1. So W net is equal to W out minus W in. So W net is equal to Cp into, we are substituting these things. Cp into T3 minus T4 minus Cp into T2 minus T1. Or you are writing it as, say, you are taking temperature ratios. So Cp into T3 into 1 minus T4 by T3 minus Cp into T1 into T2 by T1 minus 1. Or for the temperature ratios, you are substituting the pressure ratios. So there you are getting Cp into T3 into 1 minus 1 by Rp, the whole raised to gamma minus 1 by gamma, minus Cp into T1 into Rp into gamma, Rp raised to gamma minus 1 by gamma minus 1. So I think you can, if somebody needs, they can take the screenshot. We will go to the next session and next point then. Okay, we will move to the next one where Rp is the pressure ratio. Okay, next we are having the work ratio. So in work ratio, already we have seen this is the work output, this is the work input from by the compressor, and the denominator portion is also the work output by the turbine. When you substitute all these things, there will be a simplification because these two terms are equal. So 1 minus a particular term. So there you will have all the Cp is there in numerator and denominator. We have eliminated that. So T1 by T3, T1 by T3. So at the numerator, you are having Rp, the whole raised to gamma minus 1 by gamma minus 1. And in the numerator, there is a mathematical manipulation. Just taking the LCM and taking the mathematical manipulation, you are having Rp raised to gamma minus 1 by gamma minus 1 divided by Rp raised to gamma minus 1 by gamma. So finally, you are getting 1 minus T1 by T3. Now, these two will get cancelled. This will go to the numerator. So you will have Rp raised to gamma minus 1 by gamma. So work ratio is equal to 1 minus T1 by T3 into Rp raised to gamma minus 1 by gamma. Simply we can say work ratio is equal to 1 minus the temperature ratios multiplied by the pressure ratio raised to gamma minus 1 by gamma. We are concluding it like this. Already we have derived two terms related to the performance of gas turbines. First one was the thermal efficiency. The thermal efficiency is a function of pressure ratio alone. But the work ratio is a function of pressure ratio and temperature ratio. And we can see that if you closely observe this equation, we can say when T1 is minimum, because it is 1 minus something. So when T1 is minimum, or the inlet air temperature, that is inlet air temperature. So if the inlet air temperature is minimum and the maximum temperature, that is the temperature at the end of combustion, is maximum, then you can say it is the ideal condition or maximum work ratio you will get. If you want, you can just take the screenshot. Now we are going to the pressure ratio for optimum specific output. The specific output of the turbine is already we have seen what is W net. Is the W out, that is the work by the work done by the turbine minus work done by the compressor. That part already we have seen and we know this particular part. Now always carrying this gamma minus 1 by gamma in every equation is very difficult. So we can put gamma minus 1 by gamma is equal to m. Therefore, W net is equal to Cp into T3 into 1 minus 1 by Rp raised to m. Instead of gamma minus 1 by gamma, you are writing it as m. And the next term is also having Cp into T1 into Rp raised to m minus 1. So how you will get the maximum specific output? For getting maximum specific output, the parameter is actually the pressure ratio. So to get the maximum specific output, you have to differentiate the above equation. Already we got this equation. So this equation should be differentiated and equated to 0. For maximizing, that is the procedure. You know the mathematics. So based on that, you will get the condition for the optimum condition of the pressure ratio. Here you can see the dou by dou Rp of W net. So based on this, you will get these two terms we are getting or equating to 0. So finally you will get mCp T3 into Rp the whole raised to minus m minus 1 mCp T1 Rp m minus 1. So here T3 by T1 is equal to Rp the raised to, okay, that is a simple mathematical just manipulation. So T3 by T1 is equal to Rp raised to 2m. So, or we need Rp, that is pressure ratio, because pressure ratio is the parameter which we are going to study to optimize or to maximize the specific work output. So Rp is equal to T3 by T1 the whole raised to 1 by 2m, or it will become, because m is equal to gamma minus 1 by gamma. So this will become Rp is equal to T3 by T1 the whole raised to gamma by 2 into gamma minus 1. You can, if you want, you can take a screenshot. So that derivation is completely given here. Now, so far we have discussed about ideal gas turbine cycle, but we have to come to the actual situation. We are not coming purely to actual conditions, but we are avoiding some of the ideal situations. Especially, we are having isentropic compression and isentropic expansion, which is not at all possible. So the actual compression in the compressor and expansion in the turbines are not isentropic. Here you can see that HS diagram. You have studied HS diagram in your thermal engineering initially. So here you can see this is the specific enthalpy and this is the specific entropy. So here this 1 to 2, or you can say it as 1 to 2 dash. 1 to 2 dash, here it is written as 2s, but you consider it as 2 dash because in the equations I have given as 2 dash. So 1 to 2 dash is an isentropic process, but actually it will be 1 to 2. So if you draw two horizontal lines from 1 and 2, and you draw another line from 2 dash, you can see that delta H for this one, what is that? This is the non-isentropic line. The non-isentropic line requires more work in the case of compressor. So Cp into T2 dash minus T1 is less than Cp into T2 minus T1. So what is the isentropic efficiency of the compressor? Isentropic efficiency will be equal to these two terms you can write. So Cp will get cancelled. So finally you will get T2 dash minus T1 divided by T2 minus T1. Similarly, you will get the actual gas turbine. In actual gas turbine, in actual gas turbine, the turbine part, there you are having 3 to 4 S. It is an ideal situation. For us, I have written here as 4 dash, but here it is 3 to 4. So 3 to 4 is the work which is obtaining. Really, we are getting only H3 minus H4. But theoretically we are saying it is H3 minus H4. So work output is less compared to the isentropic expansion. So the actual work by compression is Cp into T3 minus T4. In comparison, we will get the efficiency of the turbine is equal to T3 minus T4 dash divided by T3 minus T4. So combining all this particular curve will give you almost an actual situation. That is 1 to 2, not 2 dash. Then 2 to 3. Then 3 to 4. So 1 to 2 and 3 to 4 are non-isometric curves. Sorry, non-isentropic curves. Non-isentropic curves. So non-isentropic curves means they are all away from the ideal situation. I think now it is clear to you. If you want, you can have the screenshot. Now we will move to a problem. Let us have our first problem. This is actually a KTU question in December 2018. Air enters the compressor of a gas turbine plant operating on Brayton cycle at 1 bar and 30 degrees Celsius. The pressure ratio in the cycle is 7. Calculate the maximum temperature in the cycle and the cycle efficiency. Assume turbine work is 2.5 times the compressor work. Take the ratio of specific heats as 1.4. So what are the things given in this question? It is given that, see, air enters the compressor of a gas turbine plant operating on Brayton cycle at 1 bar. Now, the initial temperature is 30 degrees Celsius or it is 303 Kelvin. The pressure ratio is given, that is Rp, P2 by P1 is equal to 7. Now, one condition is given, the maximum temperature that is the what we have to find out. Here it is given, assume the turbine work is 2.5 times the compressor work. That means W out is equal to 2.5 W in. Earlier I have mentioned gamma. Gamma is equal to 1.4 for air. The medium is air. Even if it is not given as 1.4, you have to take it as 1.4 if the medium is air. Now, what are the things we have to find out? The question is asked to calculate the maximum temperature. Why I have written it as T3? Here you can see 1 is the inlet temperature at the compressor, 2 is the exit portion of the compressor, and 3 is the exit of the combustion chamber where you are getting the maximum temperature. So you have to calculate T3. After that, you are having T4. T4 is the exit of the gas turbine. Then you have to find out the cycle efficiency. First, we will start with how to find out T3. So to find out T3, we know the relation. Already we have considered this relation in the derivation. That is T3 by T4 is equal to T2 by T1 is equal to P2 by P1 the whole raised to gamma minus 1 by gamma. Where you can see T3, see the first part we can avoid because we don't know T3 or T4. But here T2 is not given, but T1 is given. We know the value of gamma, then the pressure ratio is 7. So P2 by P1 is 7. Based on this, you will get T2. T2 is equal to 527.59 Kelvin. Now, W in is equal to, or the compressor work input is equal to Cp into T2 minus T1. Already we are having T2 and T1. T2 we found, T1 is given. So now the value of Cp is equal to 1.005 kilojoule per kilogram Kelvin. This you have to study because Cp, specific heat of air, is 1.005. Cv is equal to 0.718 and gamma value is equal to 1.4. This you have to understand even if it is not given in the question. So W in is equal to 1.005 into the values T3, T2 and T1 you have substituted and you will get 228.73 kilowatt. This is for unit. I have used the unit as kilowatt because I have considered unit mass flow rate. If you are not considering the mass flow rate, then you can simply put it as kilojoule per kilogram also. So what is W out? In the question it is given that it is 2.5 times that of W in. So that you can directly calculate, you will get that as 571.83 kilowatt. So what is W out? It is equal to Cp into T3 minus T4. And T3 already now we are having Cp. T3 and T4 are unknowns. So T3 minus T4 you will get a value that is 568.98 because W out is out, you know, Cp you know. Here you are having T3 by T4 which is equal to 1.74. So you are having two unknowns and two equations. Solving 1 and 2, simply you can solve this and you will get T3 is equal to 1337.87 and T4 is equal to 768.89 Kelvin. Okay. Of this, the first value, that is T3, is the first part of the question. Now we have to find out the efficiency. So efficiency is equal to, simply it is W net by Q in. Okay, so it is W out by minus W in by Q in. Q in, you know, it is Cp into T3 minus T2. That is the maximum temperature minus the exit temperature of the compressor. There you will get 1.005 into 1337.87. Okay, you will have the calculations. Finally, you will get this as 814.33 kilowatt. When you substitute W out, W in, and Q in, all these values are with you because you have calculated these things. We have obtained these things in the last slide. So you will get eta is equal to 43.13. So that is the second part of the question. So now you got T3, that is the first part of the question, that is 1337.87 Kelvin, and efficiency is equal to 42.13%. So that is the question. I think these parts are clear to you. Shall we proceed to the next problem? Now you are having the second problem. Okay, thank you. This is question number 2. In the previous question, we haven't considered about the compressor efficiency or the turbine efficiency. Here, in this problem, we are going to consider the compressor efficiency and the turbine efficiency. The question is, air enters the compressor of a gas turbine plant operating on Brayton cycle at 1 bar pressure and 300 Kelvin temperature. The pressure ratio is 5 and the maximum cycle temperature is limited to 1075 Kelvin. The compressor and turbine efficiencies are 80% and 85% respectively. Make calculations for the net work output, cycle efficiency, and the work ratio. So what are the things given? Here P1 is given as 1 bar. T1 is given as 300 Kelvin. That is also shown here. Now you are having the pressure ratio as 5, Rp is equal to 5. The maximum cycle temperature, last we have seen it as T3 is the maximum cycle temperature. In the last problem we have seen that is 1075 Kelvin. And if the compressor and turbine efficiencies, eta C is equal to 80% and eta T is equal to 85%. These are the things given in the question. You have to find out net work output, that is W net, cycle efficiency eta, and work ratio. So how to solve this problem? To find the net work done, W net is equal to, the general equation we can write, W out minus W in. That is equal to Cp into T3 minus T4 minus Cp into T2 minus T1. Of these, T4 and T2 both are unknowns for us. We are having T3 and T1. So we have to find out T4 and T2 separately. For finding T2, we should have, because T2 is the outcome of non-isentropic lines. Sorry for that. Non-isentropic line, isn't it? So 1 to 2 is non-isentropic line. You cannot straight away find out that. So first you have to consider the isentropic curve, that is 1 to 2 dash. Based on that, you will have T2 dash by T1, which is equal to P2 by P1, the whole raised to gamma minus 1 by gamma. We know, already I have mentioned that for air, gamma is equal to 1.4. So T2 dash by 300 is equal to 5 raised to 1.4 minus 1 by 1.4. So you will get T2 dash is equal to 475.36 Kelvin. If you want, you can take the screenshot.
Sir, hello, sir.
Yes, Redip.
Okay, sir. Salman has asked to show the slide once again for question number 2.
Question, isn't it?
Yeah, question number 2. He wants to see the slide once again.
Okay. I will show. Yeah, this is the question. Is it enough?
Okay, fine. Here is okay, fine.
Okay, we will proceed.
Okay, sir.
Okay, now we are going to find out T2. T2 is equal to 475.36 Kelvin. So from that ratio, you are getting that. Next, again we are proceeding to find out the net work net work done. Here we are having the compressor efficiency, which is given. It is 80%, which is equal to T2 dash minus T1 divided by T2 minus T1. So substituting all the values, because T2 dash already you have found out, T1 given in the question, 0.8, that is the compressor efficiency is given in the question. So you will get T2. T2 is equal to 519.2 Kelvin. Next you are having, say you have to find out, you are having T3, but you need T4 dash. Because directly you won't get T4 because it is a non-isentropic curve. So we have to go for an isentropic relation, that is T3 by T4 dash, which is equal to P2 by P1, the whole raised to gamma minus 1 by gamma. Again, you are substituting T3 pressure ratio, and you will get as T4. You will get T4 dash as 678.43. If you want, you can take the screenshot. I think we can proceed. Again, we are proceeding to find out net work done. Here, the turbine efficiency is given, that is T3 minus T4 dash divided by T3 minus T4. There, you are already having T3. T4 dash you have found from the last slide. Now, the only unknown is T4. This is T4. So you will get T4 as 737.92 Kelvin. And there is Kelvin. Okay. W net is equal to Cp into T2 minus T1 minus Cp into T3 minus T4. Now all the terms are there. Cp value, 1.005 kilojoule per kilogram Kelvin for air. Then T2 we have found out. T4 we have found out. So you can substitute all the things, and you will get finally W net is equal to 118.47 kilojoule per kilogram. you want, you can take the screenshot. Next, we can have.
Hello, sir. We are moving to the last 5 minutes.
Yeah. I know. Within 5 minutes, we can conclude.
5 minutes of the session.
Yeah.
Okay, fine, sir.
Okay. So next we have to find out the cycle efficiency. Only some simple equations are there. That is W net by Q in. Heat supplied we know, that is Cp into T3 minus T2. So this is T3, this is T2. So when it is heat supplied, you cannot take T2 dash because it is an ideal point. You have to take T3 minus T2. T3 is known to you, T2 is known to you. So you will get finally 58.58. So now you can get the efficiency as W net already you have found out. So 118.47 divided by 558.58. So it is 21.21%. Now the work ratio, that is the last point we have to find out. Work ratio is the net work divided by the turbine work. Already you are having net work. So the only thing you have to find out is the turbine work. That also very simple. Cp into T3 minus T4. T3 minus T4, not T4 dash. It is T3 minus T4. So using that, you will get, it is 338.76 kilojoule per kilogram. So the work ratio is 118. That is net work already we are having. It is 118.47 divided by 338.76. You will get it as 34.9%. So all the three values we got, that is net work done is 118.47, cycle efficiency 21.21%, that is work ratio 34.9, that is the values. So I think I have completed whatever planned for today, and I am giving you some questions which already came for from KTU. There is some 2018 question, 2019 question. If you need, you can just take a screenshot and you can study, because already we have discussed these things in our discussion. I think now we can proceed to the question and answer section if anything is there.
Okay, sir. Sir, one of the students have asked to please show the slide of question number 1 again, so that he can take a screenshot. I think after completion of this previous year question paper, we can allow him to take the questions.
Yeah. Yeah, this is the question number 1.
Okay, sir. One of the students have asked.
Yeah.
No, he just asked to show the question again once more.
Okay,
sir. Then one of the students have asked, Apurni, is derivation important for exams?
Yeah, derivation is important.
Okay.
Many times in the last the question set which I have shown, these questions are asked in KTU. These derivations are asked in the previous university.
And another question came is that?
Yeah.
Okay, fine. That's his question. And then another question is compression ratio and pressure ratio is same? A person named Justin P. Johnson have asked that.
Which one? I am not getting.
A student named Justin P. Johnson have asked whether compression ratio and pressure ratios are same. So he want to know the difference between both, or he want to know whether both of them are same.
Both of them are same.
Okay, I think there are no more questions in the question answer session.
Yeah.
Okay, fine. I think we can wind up now.
Okay. Thank you for listening.
Okay. Thank you, sir, for this informative class.